There are some processes you can use. The most important one is the so-called soil gel process. That was already discovered in the late 1930s by the glass manufacturer Schott in Jena. And you can do like thin films on glass or on any other surface. But then what they discovered in the 80s, if you take these small nanoparticles, you see the bigger things on the right-hand side. These are nanoparticles, just like, let's say, 10, 20 nanometers across. If you put some organic molecules on that, and then you go through the whole process, you can create these easy-to-clean surfaces. I think most of you know that, scratch-resistant, all that. That's already there. That's not a future application anymore. And you see in the upper picture, you see the soil, which is water molecules and the nanoparticles. And then you just remove the water, and then the nanoparticles start to form a network. And if you put this onto a surface as a very thin film that's maybe a few hundred nanometers thick, then by this physical principle of self-organizations, all these molecules that you have attached to the nanoparticles, then they will just stand up. It's like that you have a meadow of molecules, and these molecules all together, they create this effect that water doesn't stick to it or whatever. This is the whole secret behind these functional surfaces, as they are called. But another interesting thing that you can do with this self-organization, where structures are just created by themselves, you don't do really much with that. You just heat it up a bit or give that some thermodynamic conditions, and then you will create a structure. What you can do, was done the first time in the early 90s, that you can take small strands of DNA, which is in everybody's genome. And you know that's always two strands, they are like a ladder, which is like a helix twisted. But if you take just one of them, and then you look carefully at the order of these bases that you see, CA, C, G, all that, then you can create other strands that have the complementary bases. And suddenly you form new structures that have not been there in nature. This is not a helix anymore. This cross is called Halliday junction. And then, of course, you can go on and create bigger scaffolds, bigger patterns like on the right side. And the idea behind is that maybe one day they could use this to assemble processors. They attach transistors to these DNA strands, and then they just put everything together, wait a bit, and it assembles by itself. Because if you think about moving all these tiny transistors with a scanning tunneling microscope, each separately, then I think it would take you 100,000 years or a million years. So this is like a first kind of nano building. This is really something new that had not been done before. Of course, they discovered some interesting particles. I think the two of them you already have seen somewhere, maybe in the media. This is carbon. Of course, these kinds of molecules have been around for millions of years, or in every campfire they are produced, just by chance, but nobody knew that they existed. Everybody knew there was diamond, there was graphite, and there was just plain carbon. And then in 1985, they first discovered the buckyball. This is the football on the right side, because it's exactly 60 atoms in the pattern of a football, which I like very much, because the actual football was introduced in '74 at the German championship, and 11 years later, they rediscovered it in the nanoscale. And the other one on the right side, this is the so-called nanotube, which is similar pattern from hexagons of carbon atoms, plus 2 half spheres at the end. They can be very long, like micrometers, but they're only one nanometer in diameter. And the interesting thing about these nanotubes, they are like, let's say, they are a kind of superstar of nanomaterials. That they have a better electrical conductivity than copper, better thermal conductivity than diamond. They are stronger than steel. You can already put them together, spinning nanotube fibers out of them. You can make sheets, foils that resemble a little bit this stuff that you use in your refrigerator to keep things fresh. It's transparent, but if you put a voltage at the foil, at the sheet, then it starts glowing, emitting light or heat. And you can do some funny things with these nanotubes. But it's all not yet on an industrial scale. It's all like you could do that in principle. So this is more like, let's say, in the next 5 to 10 years, you will see something coming out of that. So the second thing, what can you already do? Well, this is a lot of parts. It's 12 different applications. I don't want to mention all of them. But the most important thing about that is it's all materials. It's not yet nanosystems that you say you have complex structures, like the ribosome, for instance. That's kind of a machinery. It's only, you put some nanoparticles in metals, in plastic or whatever, and then you create a new property. And, well, you have these stain-repellent fabrics, that's 4 and 5 in textiles. That's already on the market. There are some companies, the most successful one is called NanoTech, like Gore-Tex. They knew how to name that. And then you have, let's say, 10 magnetic layers for compact data memory. That's in everybody's hard drive already, the giant magnetoresistance effect that was discovered in the 80s and was perfected for industrial production in the late 90s. So in every today's hard drives, you have, in this sense, a nano component. So let's just show you a few applications, nanosensors. That's tiny structures that can react on single molecules, even single molecules. One very popular one is these cantilever arrays on the left side, where you put some molecules like biomolecules on, and if they attach together, then the cantilever is bent down. And this bending down you can read from a reflected laser beam, which is reflected differently if it's attached or not. So if the laser is reflected then differently, then you know, okay, there is something in the probe. Another thing is quantum dots. These are nanoparticles, let's say, like 5 to 20 nanometers in diameter, semiconductors. And they have a strange electronic structure. So what you can do is, if you attach, for instance, a DNA strand of anthrax in this hairpin mode on the left, and then you have one of these famous letters, and you put this stuff in, and if it's anthrax, then the complementary DNA strand attaches to this hairpin, the hairpin stretches out, and by this process, the quantum dot is activated, so that when you shine light on this quantum dot, it will re-emit light, and you will see a glow, and you can immediately say, well, that's anthrax. And that's already there, both of them. This is already products. It's not a concept anymore. Nanoelectronics, I mean, I don't have to tell you about the end of Moore's law and the problems of miniaturization in the next 10 years, maybe around 2015, when photolithography can't achieve that you have transistor features that are smaller than, let's say, 30, 40 nanometers. So there are a few different concepts. One is the millipede, which is developed so far that IBM could put it out as a product. They don't know if they want to do it already, because they don't know if there's a market or not. It's a bit like the early days of computing, that you have punch cards and you punch in with these cantilever tips small holes, and the holes represent the bits, and the diameter of one hole is 15 nanometers. So that means that even on the area of a coin, you could have, let's say, a few DVDs if it works. At the moment, the prototype is it's about 4,000 of these cantilevers. Of course, that's not enough. You would have more like millions of these cantilevers. The second is the crossbar latch by Hewlett-Packard. That's more like a prototype. It's not as far as the millipede. This is a real molecular electronics concept, because you see these funny things in the middle. This is just a very big molecule. It's called rotaxane. And this molecule can have two separate states. The ring can either be further down or further up. And then you could say, well, if it's up, it's a bit value 1, or if it's down, it's a bit value 0. And they have built already a prototype that is working quite well. But then, of course, nobody knows how many years it will take if we have like a crossbar latch in a computer or for storage or whatever. Third thing is the nanotubes that I already mentioned. This is what you see, the blue line. This is a nanotube, and then you have a good comparison. These other big bars, these are the gold electrodes, and they have more the format of transistor features or electrode circuits on a processor as it is today. And then you can see the size difference. The only problem is this is only one nanotube transistor, so how do you integrate millions of them? And nobody knows this. And for that reason, they hope that they could do it, for instance, with these DNA scaffolds that I already showed you. Another interesting thing is are the nanosolar cells. It's a kind of artificial photosynthesis that was discovered in the 1980s by Michael Grätzel in Switzerland. And he discovered that if he puts together titanium dioxide nanoparticles and certain dye molecules, that the dye molecules, they harvest the sunlight, then they get excited, I mean in the electronic states, transfer energy to the nanoparticles, and these titanium dioxide particles are semiconductors as well, so the electrons are moved into the conduction band. And so this could create a current. And this already works. There are several companies out there who are, let's say, they are very near making a nanosolar cell product out of it. The efficiency is not as high as in conventional solar cells. It's only 10%, but you have to know that they absorb the whole range of daylight, all the different wavelengths, in contrast to what you have in traditional conventional solar cells. So if you look at this, then you could say they are already as good as the conventional ones. And the advantage is, of course, that it's very tiny, it's very flat. It's like 200 nanometers thick, this solar cell surface, or at the biggest 2 micrometers. And it could be flexible. They just put it onto a plastic film, and some even dream that you can paint your walls with a solar cell wall, and then you can harvest just sunlight energy. Would be very nice. Another thing is nanobiotechnology. This is a very crazy concept that works really well. That was discovered by a chemist, an American chemist, Angela Belcher. She now works at the MIT. What she did was she took a very simple virus, 880 nanometers long, and it's got only a few genes. You can see this ring on the right side. And one of the genes is responsible for the protein code that this virus has. So if they insert DNA strands just at random into the gene,